Disk wins, hoop wins. It's okay. So we have votes for all, but no E. Okay, so I'll take that as a victory. Let's try it. Okay, fine. Let's try that again. The disk cheated, yeah. It rolled faster. Oh no.
It's done with physics.
So why did the runaway disk win?
It has less.
Why did the runaway disk win? Is that a stretch? I was afraid. Kevin.
Torque is equal to the change in angular momentum. So,
Okay.
as we know, angular momentum is the time derivative of angular momentum would be the time derivative of I omega, which would be I alpha. So, since disk has a smaller moment inertia thing, it would be accelerated faster, but it would have the same rate of torque due to gravity.
Okay, so he's relying on last time when we had torque is the thing that changes angular momentum. Somebody have a different way of looking at it? Dare I, Ian? All right, Ian.
Alternatively, we know that inertia is the tendency for it to stay still.
Yep.
Because we know that the disk has a lower inertia, it's half that of the hoop. That means it'll move. It'll be more ready.
He's saying that the disk has half the inertia of the hoop, but he meant moment of inertia. Okay, so for a given rate of rotation, the disk is storing less energy, less kinetic energy in rotation about the center. So as they fall, for the same distance of fall, they've lost the same amount of gravitational potential, so that's got to show up in kinetic energy of some form. So the hoop puts a lot of it in going around because it's got its mass all out there at the edges. And the disk has got a lot of the mass much closer to the axis of rotation, and so it doesn't put as much into this term. So if the sum has to be the same for any distance fallen, and the disk is putting more relatively in translation than rotation compared to the hoop, the disk should go faster.